Hello there, meteorology students. Dr. John Schrage here, and I'm here today to talk to you about one of the most important rules in meteorology. It's called the thermal-wind relationship. Now let me give you a little background here. It's really the thermal-wind equation. And the thermal-wind equation is a mess. We're not going to look at the equation itself, and it's an important rule in meteorology. It explains a lot of important phenomena that happen in the atmosphere. Because the thermal-wind relationship is fundamentally an explanation as to why winds change with respect to height. In other words, why we have wind shear. Now this isn't going to apply like right near the surface, associated with like a wind turbine or something like that. We're talking about like up in the atmosphere, say up in the troposphere someplace, up high above the ground, maybe a few kilometers up. Why are the winds changing with respect to height up there? Now we're going to use this as a way of understanding one of the jet streams. In this context, we're going to be using it to explain the mid-latitude jet stream. But you could use the same kind of explanation to explain how hurricanes work, or how wind shear happens on like the margins of the Sahara Desert, or the thermal wind equation and the thermal wind relationship are just the handiest tools meteorologists have in their pockets in some ways. We're going to be applying it, though, specifically to the mid-latitude jet stream in this context. And what we're going to see, just to kind of give you a little spoiler, is that there's going to be a polar front at the surface. Now remember, we've talked about this idea of a polar front before. It's this boundary between cold air masses that are coming from the north and warmer air that's coming from the south. We will learn that this is cold fronts and warm fronts and so on. But this polar front is someplace at the surface, and we know that there will be temperature differences across the polar front. These temperature differences are going to create differences in what are known as the thickness of the atmosphere. We'll talk about that in just a moment. Between the north and the south sides of the polar front. On the cold side, there'll be one value for the thickness, and on the warm side of the front, there'll be a different value of the thickness. And these differences in thicknesses are going to create pressure gradients and pressure gradient forces aloft. Not necessarily at the surface. At the surface where the front is, there won't necessarily be these pressure gradient forces that are being created by this. But aloft, like in the upper troposphere, there will be. And these are going to be pushing from the warm side of the front towards the cold side of the front. And then, because the winds at those levels are going to be geostrophic, we're going to set up, well, okay, if we've got a pressure gradient force doing this strange thing, apparently we have a Coriolis force doing the equal and opposite thing, and then this is going to result in creating this very strong wind directly above the polar front. In other words, there will be a mid-latitude jet stream directly above the polar front. So I've kind of spoiled for you exactly where this is going to be going, but to get there, we need to do a thought experiment. So now, what I have here, it's a little bit badly drawn in PowerPoint, but I'm trying to illustrate like we have a column of air. A column of air is a tool that meteorologists use, kind of like an air parcel, except a column of air can be quite tall, okay? We're going to just talk about like it could be extending even kilometers tall here, but we just sort of have a column of air here. That's what my little box that I tried to draw there in PowerPoint is. And let's say that the base of that column is going to be fairly close to the ground. Now, the pressure at the ground is something like 1,013 millibars on average. Let's just go with 1,000 millibars, okay? Let's just say that at the bottom of this column of air that I'm talking about, this big, tall box of air, the pressure is 1,000 millibars. And let's say this thing is pretty darn tall, and the top of it has a pressure of, say, 500 millibars. That's pretty darn tall. That would make our column of air about 5.5 kilometers tall. This is a very tall column of air here. Alright, so we got this kind of layer of air bounded by two levels. The 500 millibar level, in other words, how far above the ground you have to go for the pressure to be at 500 millibars. And the 1,000 millibar level at the surface, in other words, how far above the ground you have to go to get to a pressure of 1,000 millibars. And in between, there's this big, thick layer. Okay, it's like 5.5 kilometers thick in this case. And so, wait, I just used that word thick. This column of air has a thickness, a distance in terms of meters between the top and the bottom of it. It is the distance between the top and the bottom of this layer. It has a thickness in the same sense as like a book. A book can be a thick book or a not so thick book. Okay, not thick like as in milkshakes can be thick and gooey, or they can be runny, or whatever. It's thickness of this layer as in like the thickness of a book. It can be more thick, and therefore there's more meters between the top and the bottom of the layer, or it can be less thick, and there is fewer meters between the top and the bottom of this layer. Now, this thickness is going to turn out to be a really important property in the atmosphere, and there's lots of applications to thickness outside of the thermal-wind relationship, but that's the context in which we're learning about it at this time. Now, let's take that column of air and say, well, what would happen if we warmed that layer of air? Okay, for whatever reason, this is a warmer layer of air. How will the thickness change? Okay, the top of the layer of air still has a pressure of 500 millibars, and the bottom of the layer of air, or the column of air, still has a pressure of 1,000 millibars. Okay, we haven't done anything to the air above it, so we haven't changed the weight of the air above it, and therefore the pressures haven't changed. But the layer itself will have expanded as it got warmer. And as a consequence, well, in the terminology that we use in the atmospheric sciences, we would say that the layer has become more thick. As we warmed the layer of the air, it has expanded, it has gotten more thick. There's a greater number of meters between the bottom and the top of the layer. Now, the bottom of the layer, I mean, it's still basically at the ground. So by making the layer thicker, we've apparently pushed the height above the ground where you'll find 500 meters higher above the ground. You now have, if you're launching a weather balloon or flying an aircraft and you're looking for how high above the ground you find the pressure to be 500 millibars, it's now farther than it used to be. Okay? The thickness of the layer has increased, and 500 millibars is now higher above the ground. In the same sort of way, if we cooled that layer of air, it would start to shrink, and as that layer shrank, well, that's what we meant by thickness, right? It's still 1,000 millibars at the bottom of the layer, and it's still 500 millibars at the top of the layer, because I haven't done anything to the air above it. And remember, those pressures are just the weight of the air above it. Okay, so there's still the same pressure at the top and the bottom, but there's fewer meters between the top and the bottom of the layer. We've said that the layer has become less thick. Now, well, again, the bottom of the layer we said was basically the surface of the Earth. We haven't moved that, so it's really the 500 millibar level that's getting closer to the ground. You don't have to go as far above the ground in your aircraft or in your weather balloon or whatever in order to encounter a pressure of 500 millibars. Oh, okay. This actually turns out to be hugely important in meteorology. There's actually a great equation called the Hypsometric Equation that explains why all this works and so on. That's a term you don't need to know in this context here. But it turns out, in fact, temperature is the only factor that determines how thick a layer of the atmosphere is going to be. If you are describing a layer of the atmosphere in terms of the pressure at the top and the pressure at the bottom, like the 1,000 to 500 millibar layer, turns out the only thing that determines the thickness of that layer, the number of meters between the top and the bottom of that layer, the only thing is the temperature. I'm lying to you a little bit. It's actually something called the virtual temperature, but close enough. Your book is going to say that it's the temperature that is controlling the thickness in terms of the number of meters between the top and the bottom. It turns out it wouldn't have mattered what pressures we had chosen as being the top and the bottom of our layer. The thickness between those two pressures, let's say between the 1,000 and 850 millibar layer, the thickness between those two is going to be determined only by the average temperature between those two layers. It's actually a very useful tool. Thickness, for example, is often used by meteorologists, to determine whether a type of precipitation in the winter is going to come in the form of rain or snow. They look at the thickness of the layer that the precipitation is going to be falling through, and if the thickness is too great, they say it's going to be rain. If the thickness is small, they say it's going to be snow. The thickness? Well, it isn't really the thickness as in how many meters the snow and or rain is going to be falling through. The thickness is actually telling you the average temperature of the layer that the precipitation is going to be falling through. If the layer is not very thick, it's going to be snow because it's very cold in that layer. If the layer is very thick, it's apparently quite warm in that layer, and then the precipitation in the winter will fall as snow. As rain, rather. Thickness is a hugely important and powerful tool in the atmospheric sciences, and it's just this very cool relationship between how high above the ground pressure surfaces are going to be, like the 500 millibar surface. How high above the ground you have to go to find 500 millibars, or how high above the ground you have to find to go to be 700 millibars. Relating that to the temperature of the air below that is totally awesome. And that's what this figure from your textbook is trying to show. This is actually from an older edition of your textbook, but your textbook has a very similar figure here. And it's hard to get a sense of this perspective in here, but what they're trying to show you here is that in the tropics, a given pressure level, like say 700 millibars or something like that, is quite high above the ground, whereas if you try to follow that same pressure surface there all the way over to the poles, you would see that the 700 millibar surface is closer to the ground at the polar regions. And you could do the same game with any given level of the, like the 1000 millibar level, or the 900 millibar level, or the 500 millibar level, or whatever. They will, in general, be higher above the ground in warmer places where there's warmer air, and they will, in general, be closer to the ground in places where there's colder air. And again, the book, it's a little hard because you might think they're trying to illustrate perspective here or something like that, but that's not what they're doing here. See how the layers are thicker? There's a bigger distance between, say, 800 and 900 millibars over in the tropical region, and they're closer together in the polar region. Again, they're trying to illustrate the thickness of the layers in this diagram. Again, it's a little bit tricky because it's not the world's greatest diagram here. Okay, before we move on to part 2 of this lecture, that it ties this idea of thickness to our thermal wind relationship, and also ultimately then to why we have jet streams where we do, which is really a fancy schmancy way of saying about wind shear and how winds are changing with respect to height. Before we do any of that, let's ask a couple quick questions. Now, question 1. We could talk about the thickness of blank. What I really want to do here is I want you to understand how to use this word thickness in a sentence, okay? Are we talking about the thickness of the distance between two pressure contours or isobars on a weather map? You know, like I drew two contours on the map. Sometimes they're pretty far apart and sometimes they're close together. Is that thickness? B, we could talk about the thickness of a layer of the atmosphere bounded by a given pressure at the bottom and a given lower pressure at the top. Or C, can we talk about the thickness of individual gas molecules in the atmosphere? Is that a valid use of the word thickness? Or D, all of the above? Which of these is the right way to use the word thickness based on what we've learned so far? Make a choice from those 4 options and get a little feedback before you move on to question 2.